Hi, and welcome back. Just a quick review. In the last video, we started with this circuit, and we said it's a first-order transient circuit. We had an input voltage, a resistor R, and a capacitor C, and we also had a switch here that was open when we started, and then we said at time is equal to 0, the switch closed, and we wanted to know when that switch closed, what did the output voltage, the voltage across our capacitor, look like as a function of time? So we are looking for something that is a function of time. We're not looking for like one number here. We're looking for a function. So anyway, we did that and we used nodal analysis. We said we were going to solve for our one unknown node voltage, which was our V out here. And we did our nodal analysis, and we ended up with our differential equation. So this was the differential equation that we got in the last video. So now, pretty much from here on out, all we're going to do is we're just going to try to solve this using techniques of differential equations here. So hopefully you've had differential equations before. I'd say it's pretty important going through a circuits class to understand differential equations. I'm going to go through all the different differential equation stuff you need to be able to solve this here. But if you're feeling rusty on differential equations, it's a really good idea to go to the Khan Academy and watch the differential equations playlist. The differential equations playlist on the Khan Academy is great. And it's also pretty short, like in relation to some of their other differential equations. And it covers like literally all the differential equations you need for pretty much all of circuit analysis. So anyway, with that said, let's go ahead and start solving this differential equation. So now, the first thing I just want to say real quick is that V0 is our function that we're solving for, right? So if I wanted to rewrite this, let me just go ahead and rewrite this saying that, how do I want to rewrite this? Let's say I rewrote this where I'm going to say that x is equal to, or else actually no, let me say y is going to be equal to v0. So if I just make that substitution right here, this is going to look very, very familiar. So let me just go ahead and make that substitution real quick. Our input voltage Vi is going to be equal to RC times dy dt plus y. So now this is, if this V0 was confusing you at all, maybe this will make it a little bit easier. That we are trying to solve for y. We are trying to solve for y as a function of time. This is what we're trying to solve for. So now, and actually, you know what? I'm not going to make that substitution. Just keep that in the back of your mind. You know, what we are solving for here is this V0. Where that is our function that we're trying to get. So let me actually just go ahead and erase that, because I don't want to do that substitution. It makes things a little bit messy. So anyway, now what we have to do in order to solve this differential equation, and this applies for all differential equations when you're solving them, is that our solution that we're looking for, V0 as a function of time, that's going to be equal to everything that, or it's going to be equal to our V0 particular solution that's going to pretty much make this relationship true, and it could be a function of time, plus our V0 homogeneous as a function of time that's going to make this relationship true. And remember, V0 homogeneous, hopefully this isn't the first time that you're hearing this, but all V0 homogeneous means is the relationship where instead of having Vi on the left-hand side over here, the homogeneous relationship, I'll just underline this in yellow, the homogeneous relationship is just the relationship where instead of Vi over here, we have got 0 equals RC dV0 by dt plus V0. And it's okay if this doesn't make a lot of sense for you right now, but keep in mind, when we say that our left-hand side is equal to V0, really it's equal to 0 plus, or sorry, when the left-hand side is equal to VI, it's really equal to 0 plus VI, right? So if we want to cover everything, that V0 could possibly be, every single function of time that V0 is, to make this relationship true, we've got to cover everything that makes this equal to 0 in addition to what's going to make it equal to VI. So it turns out that what makes it equal to VI is called our particular solution. We just have to find one solution that's going to make this relationship true, that's going to make RC dV0 by dt plus V0 equal to VI. And then for our homogeneous equation, we just have to find the equation, or find the function that's going to make this relationship true. So now let's actually just start on the homogeneous equation right now, since we've got it written right here. So this is our homogeneous, and actually here, I'm going to rewrite this again. I'm going to say 0 is equal to RC times dV0H for V0 homogeneous by dt plus V0 homogeneous. So now we are solving for, and here I'm going to rewrite this, VOH for V0 homogeneous up there. So now, if we solve this relationship, if we are able to solve this differential equation, we are going to get our homogeneous solution to the differential equation. So now let's just go ahead and solve it. At this point, this is what's called a separable differential equation. It's separable because we can kind of isolate all the variables very nicely and be able to kind of integrate the thing and get our solution. So let's just do some algebra here. I'm going to take VOH over here, and I'm going to subtract it from both sides. So I'll get minus VOH is equal to RC d VOH by dt. And now, what am I going to do? Now I'm going to divide both sides by RC. So I'm going to get minus VOH divided by RC is equal to d VOH by dt. And now after I do that, I'll just keep doing each step individually. Now that I've done that, I'm going to multiply both sides by dt. So I'm going to get minus VOH divided by RC times dt is going to be equal to d VOH. And now that I've got that, I'm just going to divide both sides by VOH that I've got here. So I'm going to end up with minus 1 over RC dt is going to be equal to actually here, I'm going to write it like this. 1 over VOH d VOH. So now, hopefully you've seen this before, and hopefully you know what's coming up, but we've got dt over here, we've got dVOH over here, and just a VOH over here. So we have separated this differential equation into a form where we can integrate both sides, and the integral is going to work out very nicely. So for the left-hand side, let's do the left-hand side first. First off, we've got minus 1 over RC, right? And we're integrating with respect to t. We're integrating with respect to time. There's no t over here at all, right? So this whole minus 1 over RC, that's just a constant, right? So we could our integral really can look like that, because we just have a constant here, so the constant can move out in front of the integral. So if we integrate and if we do this, we're really integrating 1 dt. If we're integrating 1 dt, all we get is t. So the left-hand side over here is just going to be minus 1 over RC times t, times time. Now, on the right-hand side, hopefully this is familiar to you. If it's not, keep in mind, let me just rewrite this. And instead of VOH, I'm just going to replace VOH with x. What is the integral of 1 over x dx? So hopefully you remember this from, I think this was probably in Calc 1, that the integral 1 over x dx, or what when you differentiate it, gives you 1 over x. Hopefully you remember that that is the natural log of the absolute value of x plus some constant. So now, pretty much you're just going to use that we've got the same exact thing here, except instead of x's, we've got VOH here. So now, this is going to be equal to, the integral of that is just going to be the natural log of the absolute value of VOH plus some constant. We don't know what the constant is. This is just some arbitrary constant that we're going to have to solve for later. So now that we've got that, let's do a little bit more algebra to kind of clean this up. So the first thing I'm going to do is, I'm just going to multiply this t into there. So I've got minus t over RC is equal to the natural log of the absolute value of VOH plus some arbitrary constant k. The first thing I'm going to do is I'm actually going to just move this k over to the left-hand side. And now keep in mind, I could put over here minus k, but keep in mind, it's just an arbitrary constant. I don't know what this is yet. So even, like subtracting an arbitrary constant or getting rid of an arbitrary constant over here, just because it's arbitrary, we don't know what it is. I'm just going to leave it as plus k over here. So I'm going to just erase all of this stuff. I'm just going to have plus k over here. So instead of subtracting it, I'm just going to add it because it's just an arbitrary constant. I don't know what this is yet. I'm going to have to solve for it later. So now I've got minus t over RC plus some arbitrary constant k is equal to the natural log of the absolute value of VOH, of what I'm looking for. So now, how do I undo this natural log function? Well, I can exponentiate, right? I can raise e to this power. And if I raise e to that power on the right-hand side, I have to do the same thing on the left-hand side, and that is going to keep our equivalence. We're going to be able to say that these two expressions are still equivalent when I exponentiate that. So now, on the left-hand side, I've got minus t over RC plus k, all of that e raised to all of that power. Now I can use properties of exponents to just break this up a little bit. And I'll have e to the minus t over RC. And when I add two things in an exponential up here, it's going to be the same thing as multiplying. It's going to be the same thing. I can break it up in this fashion where I have e to the minus t over RC plus k can turn into e to the minus t over RC times e to the k. So that's going to be our left-hand side. And now for our right-hand side, e raised to the natural log of VOH. Keep in mind, these two functions are inverses of each other, right? They kind of undo each other. The natural log is asking e raised to what power is going to give you VOH, but then we're raising e to that power, right? So we've got the natural log of VOH is going to give us the power that we need to raise e to in order to get VOH, and then we're raising e to that power, right? So we're going to get VOH on our right-hand side. So now, we're almost done solving for the homogeneous part of this equation. The very last thing we're going to do has to do with this constant. So remember, k is just some arbitrary constant. We don't know what it is yet. We haven't solved for it yet. So if we raise e to some arbitrary constant that we don't know what it is yet, we haven't solved for it yet, e raised to some constant we don't know yet is also just some constant that we don't know yet. We can just keep on saying that this is k, right? Even though it's technically e raised to some constant, that's still just some constant we don't know yet. So we're just going to leave that as a constant k that we have got to solve for later. And I'll show you exactly how we're going to solve for that. So now, the last thing we're going to do is just rearrange this. So we're going to get k times e to the minus t over RC is going to be equal to our V out homogeneous, our VOH. So now that is the answer for the homogeneous part of our differential equation. So let me just go ahead and go back up here. So now for our answer, we just figured out what our V out homogeneous was. So let me just go ahead and rewrite what we know so far. We know that V out as a function of time is going to be equal to our V out homogeneous, which we figured out was some constant k that we don't know yet, times e raised to the minus t over RC. So now I'm out of time in this video. In the next video, we're going to cover how we're going to find our V out particular solution, and then we're pretty much going to be done. We'll have the total solution. And I also have to show you how to figure out what this constant k is. So anyway, thanks for watching, and I'll see you in a future video.